Good morning, calculus class today. So I want to talk about the 2.4, section 2.4 from James Stewart, calculus, the precise definition of a limit. So definition of a limit is always written as limit of f of x as x approaches a, so that equals L. So for the definition of the precise limit, so that would be considered if for every number, epsilon, okay, so the way to pronounce this word, epsilon. So epsilon, there's a number delta, okay, delta, it's greater than 0 such that, well, epsilon and delta, epsilon is a very small number, so epsilon is almost considered like 0.000001. Okay, so it's a very small number. It's getting close to that number. And then for delta, also, it's very small decimal. Okay. So if 0 is less than absolute value of x minus a, it's less than delta, then absolute value of the quantity f of x minus the limit, so it's less than epsilon. So now we're going to find out what this means with one of the example. So the graph is given already. So for f of x, so it's a curve. And we do have a certain position here for that 4, 5, 5.7, the x value, the y value. So using the given graph of f to find out a number delta such that if 0 is less than absolute value of x minus 5 is less than delta, then absolute value of f of x minus 3 it's less than 0.6. So anytime that you started off with the precise definition of a limit, we always want to start it off with the conclusion. Again, back to geometry. So this one is just like the conditional statement. If and then. So for the if, that means this one is the hypothesis. And then this part right here, it's the conclusion. So for example, if today is Thursday, then tomorrow is Friday. So today is Thursday, so that would be the hypothesis. Tomorrow is Friday, then that would be the conclusion. So started off with the conclusion, we do have absolute value of f of x minus 3. It's less than 0.6. So back to the concept that you learned from Algebra 1, Algebra 2. So once you break it apart, f of x minus 3, this one can be written as less than 0.6. Because you want to split it, positive, negative. And then for the negative, so we do have f of x minus 3. It's greater than negative 0.6. Okay, so now to look at that, the graph right here. So what we got is f of x, it's less than 3.6. And then for the other one here, so f of x, it's greater than f3 both sides, so we do have 2.4. So this one is right between 2.4 and 3.6. So as you can see that at 3.6, so the corresponding x value, so this one is considered 5.7. And then at 2.4, the corresponding x value, what is it? It's 4. And then once we find out the x value, so we want to plug in the number back to the hypothesis. Okay, so always start with the conclusion. So we can find out the x value. So once we get those x value, so we want to put it back into the hypothesis. So we do have 0 is less than absolute value of 5.7 minus 5. And it's less than delta. So let's find out what that is. 5.7 minus 5, so it's 0.7. So delta is actually greater than 0.7. And also we need to find out the other value. So f4, let's see what happened at f4. So this one is for x equals 5.7. And then for x equals 4, let's see what that is. So 0 is less than 4 minus 5. It's less than delta. So that means delta, it's greater than 1. So anytime that you want to find out the value of delta, you always want to choose the smallest decimal. So we want to choose this one. So delta, it's about 0.7. Okay. So that's the solution. And now, let's see what else that we have. So using a graphing calculator to find a number delta such that if absolute value of x minus pi over 4 it's less than delta, then absolute value of tangent of x minus 1 it's less than 0.2. So again, we need to start it off with the conclusion. So started off with the conclusion, we do have tangent of x minus 1, it's less than 0.2. And tangent of x minus 1, it's greater than negative 0.2. So solving for tangents, so tangent of x is less than 1.2, and then tangent of x, it's greater than 0.8. So this one is just approximation value for tangent of x. So anytime they see like less than, greater than, it's all about the approximation. So what we need to find out here is the value of x on the graphing calculator. I mean, you can use any kind of calculator for this. You can use the Google calculator. You can use scientific calculator. So here's what I want to put in. So again, the ratio, it's considered decimal. So the angle got to be in radian because that pi over 4, it's in terms of radian. It's not degree. So make sure that the calculator got to be in radian. Okay, so now let's find out what that is. So inverse of tangent of 1.2. So first thing that you always want to check. So make sure that this one got to be in radian. It is. And then we want to take that inverse of tangent. Okay, so go back to the normal window. So inverse of tangent. So what I did here, I pressed second tangent, 1.2, because we want to find out the angle. So this one is about 0.876. So just round it to 3 decimal places. So 0.876. So back to this one here. So x, it's about 0.876. And now let's plug in that the other number. So inverse of tangent of 0.8. So inverse of tangent of 0.8. So second inverse of tangent, 0.8. And for that one, we do have about 0.675. So 0.675. And now, whatever the x value that you find out, so you want to put it into the hypothesis. So let's plug in the number back to the hypothesis. So again, step 1, you always want to start up with the conclusion. And then step 2, the hypothesis. So one number at a time, so start up with 0.876. So absolute value, 0.876 minus pi over 4. And let's find out what delta is. So that's about, so 0.876 minus pi over 4. So 0.876 minus pi over 4. And, well, if this number is negative, so we want to take the absolute value of that number. This one is already in positive form, so it's 0.09. It's about 0.09. As you can see that the number is getting very close to 0. And that's the value of delta. So 0.09. And now what about for x is about 0.675. Let's find out what that is. So 0.675 minus pi over 4. Okay, let's find out what delta is. So 0.675 minus pi over 4. And take the absolute value, so that one is what, 0.110. So again, you always want to choose the smallest value for delta because that's getting very close to 0. So we're choosing this one here. So delta is about 0.09. So basically you want to find out 2 solutions for delta, but you always want to choose the one with the smallest value. Okay, so delta, it's about, or approximately, 0.09. Okay, so now let's see what else that we have for the rest of this. So the next one, the last one here, you want to prove the following statement using the epsilon delta definition of limit. So again, the definition is always saying that if 0 is less than absolute value of x minus a, it's less than delta, then 0 is less than f of x minus L, which is the value of the limit. It's less than epsilon. So for a, we need to find out the value of a, L, and the function. So for part A, so the value of a, which is considered 6. F of x, the function itself, so which is what, x over 4 plus 3, it's a linear function. And then L, which is 9 over 2. So what we want to do here, we just want to set up the conditional statement. So if 0 is less than x minus 6, it's less than delta, then 0 is less than absolute value of x plus 4 plus 3, x over 4 plus 3, minus L, which is 9 over 4. It's less than epsilon. Okay, so now let me just rewrite this one here. Less than epsilon. So again, anytime that we want to solve for delta or things that you want to prove, you always want to start it off with the conclusion. So started with the conclusion, we can combine the like term. So absolute value of x over 4, 3 minus 9 over 4, so we do have, well, 3 is considered 12 over 4, so which is what, 3 over 4. It's less than epsilon. And now the next thing that you want to do, you always want to take out the greatest common factor. So things that they share in common here, it's 1/4. Absolute value of 1/4 times absolute value of x plus 3. It's less than epsilon. And now, instead of taking out that 1/4, so you probably want to take out that 3/4, because that we need to end up with the same kind of quantity as absolute value of x minus 6. So instead of just taking out that 1/4, we want to take out 3/4. So absolute value of 3/4, so that would be 3/4. And then once you take out 3/4, so let's see what we got for this one here. Okay, so this one looks like we're going to end up with a different structure. Okay, oh, you know what? I think I put in something wrong. So L is actually 9 over 2. Excuse me. So let me fix that. So that's why you end up with something completely different. Apologize for that. So let me fix it. So this one, the value of L, the limit, is supposed to be 9 over 2. So it's supposed to be x over 4 plus 3, the function, minus the value of the limit, 9 over 2. So that's why it's less than epsilon. So now what we have here, combined the like term, we do have absolute value of x plus x over 4. And then 3, it's written as 6 over 2. 6 over 2 minus 9 over 2. So we do have negative 3 over 2. Okay, so again, so 3 here, it's considered 6 over 2 minus 9 over 2. So that's why it's negative 3 over 2. So it's less than epsilon. And this one is greater than 0. So now from here, we can take out the greatest common factors. So let's take out the constant. Or you know what? Let's just take out that 1/4. Because we need to come up with a similar structure like x minus 6. So take out that 1/4. Absolute value of 1/4. That's 1/4. So now what's left here? We do have x minus 6. Because 6 times 1/4, then that would be 3/2. So it's less than epsilon. Now, compare and contrast. So this one is quite similar. So what we need to do next, we need to isolate that absolute value of x minus 6. So absolute value of x minus 6, it's less than epsilon times 4. Or 4 times epsilon. So now, back to the hypothesis. Instead of using that absolute value of x minus 6, guess what we can use? We can use 4 times epsilon. Well, because that greater than, less than, that means it's about, it's approximation. So this one is saying that 4 times epsilon, so that it's less than delta. And now we need to solve for epsilon here in terms of delta. So that means epsilon, it's less than delta over 4. And that's the proof. As you can see that this number is very small. This number is smaller because that once you divide it by 4, so that means the decimal is getting smaller. So the proof, the purpose of doing that, we just want to show the relationship of that epsilon and delta. So once we've been able to show the relationship of epsilon and delta, so that means it's the proof. And the problem is that it won't be able to link through the process of epsilon and delta, so that means the proof would be considered disproof. So this one is called the precise limit definition for epsilon and delta. So now let's try part B right here. So the limit. So let me just put it in for the next slide. So the limit of the quadratic function. Let's see what that is. It's a x squared minus 4x plus 5. So that equals 1, and the value of x, which is 2. Okay, so making sure that everything is all correct here. So one thing that we need to find out, so the value of a, which is 2, and then f of x, is the quadratic trinomial. And then the value of L, which is what? 1. Again, let's put it into the precise definition of limit. So if 0 is less than absolute value of x minus 2, it's less than delta, then 0 is less than absolute value of f of x, which is x squared minus 4x plus 5, minus L minus 1, it's less than epsilon. So again, I'm just using the definition of limit with epsilon and delta. So put in all those elements. And now started off with the conclusion. So we do have 0, it's less than absolute value. While this one here, for the quantity, we can combine those like terms. So x squared minus 4x plus 4, it's less than epsilon. And then for the quadratic trinomial, so it looks like this one is factorable, so let's factor it. So we do have x minus 2 quantity square. It's less than epsilon. Again, we need to come up with a similar structure as this one here. So for the exponent, so what we can do here is take the square root. So that means take the square root both sides. So we do have absolute value of x minus 2. It's less than square root of epsilon. So the other way to rewrite that square root of epsilon is epsilon to the power of 1/2. So now, instead of using that absolute value of x minus 2 in the hypothesis, we're using that epsilon to the power of 1/2. So epsilon to the power of 1/2, it's less than delta. And then finally, we want to solve for epsilon. So in order to get rid of the power, so we multiply the power by 2. So that means epsilon, it's about delta square. And that's the proof. Okay, so any questions, anything that you're struggling, so things that you're stuck with the limit proof, so make sure that you need to rewind or rewatch the video. Okay, so especially the part that you're having a hard time to deal with, hypothesis, conclusion, with epsilon and delta. And thank you for watching the video today, so I'll see you guys next time.